Okay, welcome everyone to the first SIP seminar of spring semester. It took us a while to get started, but we couldn't have picked a better person to kick off the spring series. It's a pleasure to have Ulugbek Kamilov join us from Washington University, St. Louis, to give us a talk on computational imaging, reconciling physical and learned models. Just as a background about Ulugbek, he did his PhD from EPFL in 2015, and then he moved to Mitsubishi Electric Research Lab as a research scientist and worked there for a couple of years. I guess he was missing the academic world, came back to it, joined Washington University, St. Louis in 2007. And has been doing phenomenal work there in the general areas of computational imaging and has received a number of recognitions for his work. But the icing on the cake right now is that he just got awarded about, I guess, a month or so ago, the prestigious NSF Career Award. So congratulations on that. I'm pretty sure it's a, as a junior faculty, it's always a relief, although you don't look like or feel like junior to me. We have known each other for a while. So it's a real pleasure that he was able to find time to come and talk to us about a lot of interesting things that he has been doing, which is reconciling physical and models and deep learning kind of models. And without further ado, I'll hand it over to him. Thank you.
Thank you, Wahid, and thank you everybody for joining in this. I'm really excited to talk to everyone. So the title of my talk, Reconciling in Physical and Learned Models, is going to get a little clearer as we go along. But essentially, as Wahid said, we're going to talk elements of deep learning, but we're going to talk about elements of whatever we used to do in image reconstruction, which is model-based image reconstruction. So we'll try to bring those two things together. Now, to kick off this talk, let me start with obvious. Machine learning will change imaging technology, but the technology is still at its infancy. And every talk, I like to give examples, weird examples where things don't work as we expect. And this is a funny one that some of us here, I know, are active on Twitter, probably have seen this. At some moment, there was a team that shared this nice video of this image super resolution algorithms that would take an image which is completely pixelated, use a generative model to try to generate a high-resolution image that keeps consistency with kind of original pixelated image. That was kind of a claim. But then, of course, Twitter being Twitter, people came up with lots of interesting counterexamples by using this tool. And this was one where somebody tried to use a photo of President Obama and tried to super resolve him and got somebody who's not exactly like President Obama, right? And then people try to repeat this experiment over and over and over, and then each time, recovering somebody else who is clearly not Obama. So all I wanted to say with this little introduction is that this is a very active research area, but we're all kind of going around this topic of trying to understand where things work, where they don't work, what can we understand, how we can extend things, and so on. And this is going to kind of fall in line with my talk. But my talk really is going to focus on biomedical imaging. Although it's not going to strictly be biomedical imaging, but it could go beyond. But I'm going to focus on biomedical imaging just because all the applications I'm going to show you will be in biomedical imaging. Okay, so if you take biomedical imaging in general, if you go in the past, it really used to be only a hardware exercise, right? What do I mean by hardware exercise? Originally, it was all about designing hardware. You would try to make a microscope where you map a point somewhere in space to an eyepiece so somebody can look at it and see kind of a closer object. Or you could try to map it to film, take a photo and record it, right? That was kind of original perspective on image formation. Now, what happened later is we got computers that improved our lives and giving us a little bit of comfort of post-processing digitally, right? So now we could record things digitally and then now write algorithms that would do something on these digital values. For example, we could enhance things, we could highlight things, we could segment things, and so on. So that was essentially where things moved by having digital image processing. Now, in the near future, we're now seems like moving to the third direction, and many of us here in this talk and in the community are contributing in this direction, where now we're trying to get the data from an instrument. Okay, we have still computers that can digitally process it, but we don't use the data only coming from instrument. We combine it with data that's aggregated from some large external data sets. So for example, this could be some machine learning model trained on a data set that now gets combined with this individual data from instrument to try to extract more than we have just in those measurements, right? So now there is this whole data aggregation process, which is essentially where machine learning kind of nicely fitting in. And this is kind of the direction my talk is going to go to. And this is essentially the direction my group has been working in the past few years, right? So in the context of biomedical imaging, today I really want to talk to you about the inverse problems. So inverse problems in biomedical imaging. Many people might be familiar with inverse problems. If you're not familiar, inverse problems is specific type of problems where the goal is to infer something that we don't know. So that's the red thing you have. I don't know it, but I want to obtain this. This could be an image, some kind of desired image in microscopy, or it could be some parameters you want to infer also. Now, the forward problems, this is what I'm going to refer to, refers to the mapping between what we want to have to what we actually obtain, which are the measurements y. Now, H here is the forward model. It's an instrument, it's a model of an instrument which could be nonlinear or linear mappings, that's mapped here, written here, which essentially encodes or puts together the physical information, the physics that we know, right? And I'm going to give you a couple of examples very soon. And then, of course, we also have some noise because nothing we do is ideal. So finally, the forward problem can be written as an application of this operator H plus noise. Now, what we want to do is once we have the Y, we want to get back X, and that's the inverse problem. This is what I really want to talk about. We want to recover X given the measurements Y. Okay, now the reason I'm going to talk about inverse problems, and I really like this formulation, is because it's a very unified way of talking about many problems. And this is what I do. I'm an algorithms guy with a signal processing background. What I do is I write algorithms and then I look for ways to apply those algorithms to applications, and very often biomedical applications. And since I'm at Washington University, which is one of the leading medical institutions, this gets me a natural connection with the medical school campus. So here you have lots of examples where you have a forward model characterization for different types of imaging instruments and modalities. Okay, so let me give you two specific examples I'm going to talk to you today. So magnetic resonance imaging. So magnetic resonance imaging is an example where the physics is very complicated, but the way data collection happens is we don't collect data directly in the image space, like in the cameras, right? In the cameras, I collect things directly in the image space, but we collect it in the Fourier space, or the so-called K space. So it's a sequential process. By collecting more and more data in the K space, we form higher and higher quality images by taking inverse Fourier transform, right? So this is a magnetic resonance. And of course, since the process is indirect and sequential, it takes time to collect the data. And the longer data collection, of course, leads to better images because you can mitigate better noise and have less artifacts. But it also implies more discomfort for patients because they have to be inside that machine for longer time. All right. So here's some examples of what it means to have shorter and shorter scans. So this is from data that we have reported in this publication. But here you have 1 minute scan, 2 minute scan, and the full scan, which could be anywhere between 5 minutes to 20 minutes, depending on the type of MRI images I'm talking about. But you can see that if you undersample or do faster scans, we have to deal with this kind of artifacts. But 1 minute would be definitely more desirable than 20 minutes in practice. And the second example is, let's say, tomography, computerized tomography, or any type of tomographic imaging, where now, instead of collecting things in the Fourier space, we collect data in the sinogram space. So what you see on the left is what we call sinogram. Essentially, each column here corresponds to a single projections of the image. And then it can be characterized as a radon transform, that's a forward model. And you can use a filter back projection to bring it back to the image space. And you can see again that more projections leads to better images, but more projections means also you have higher X-ray radiation. focus on the patient. If it's medical, it could also mean that you expose the cells to higher radiation if you do microscopy. And also materials means you expose higher radiation dose on different materials if you do material imaging with X-rays. Okay, so here are some examples of having different number of projections. Again, if you try to reduce number of projections, at some moment you have to start dealing with artifacts. And then if you take more and more projections, you reduce artifacts. All right, so those are the two examples. Let me talk about three challenges that we want to address in today's talk, right? The first challenge in all this inverse problem world is a slow acquisition problem. So why do we have slow acquisition? Because the modalities I'm going to talk about, all of them are sequential and indirect. So we collect the data sequentially in another domain than the image space, all right, indirectly. And then this means to get more data, we have to do this slower. So the goal is to try to make it as fast as we can. So here's a little example from a tomographic microscopy, but we don't need to go too deep inside that. The second challenge is imaging artifacts. And I showed you some examples, but you can get tons of examples. If you do a fast scan because of you have to, or like, for example, this is an example from free breathing MRI, where a person breathes, we do one 3D scan, we try to separate it into different motion states. Now, this problem cannot be not undersampled just because of the motion, right? And in any problem like this, you'll have to deal with imaging artifacts because of undersampling, model mismatch, or noise. This is a problem we have to deal with. And finally, high computational and memory requirements. This is very easy to understand. Essentially, we have two types of challenges. We have a large measurement challenge, which means we have to deal with a lot of measurements, and a large image challenge when we have to deal with big images. So a large image challenge might mean we do 3D images, which is space. 4D could be space and time, so 3D videos, or 5D, which could be space, time, spectral images, so which can go anywhere to 10 to the 6 to 10 to the 12 voxels, right? And a large measurement challenge means we have collection of data, which is indirect. So here you could collect 2D projections of this nice 3D algae, and each image is going to be 1 megapixel, and you can end up anywhere between 100 and million of those images to process, right? So those are the three challenges I want to address, and this is all, in fact, part of my NSF career proposal that I've been working on, and it's a topic I'm going to continue working in the near future. So today, basically, I'm going to talk to you about three things. The first thing is going to be the concept of regularization by artifact removal, which is a methodology that can integrate physical models, which are the forward models of the imaging instruments, and deep learning models as prior information sources. Okay, that's going to be the first. In the second talk, we're going to talk about how to design incremental or stochastic version of rare type of algorithms that allow us to scale the computation up. And in particular, we're going to talk about the idea of building unfolded model-based networks where we do approximate physical layers that use kind of incremental processing within them. So that's going to be the second. And finally, the third topic is related to this whole interest around the topic of neural representation. So lately, if you go on Twitter or you look at papers, a lot of people have been working in the area with a thing called NERF, so neural representation fields. And essentially, COIL is a relative of that, where we use that concept to try to come up with self-supervised learning method to represent measurement fields in computational imaging. And I'm going to talk to you about third section of my talk. All right. So let me get started with a rare idea. So, and to kick things off, let's talk about a very simple recipe to train neural networks in computational imaging. Okay. So let me explain you this thing you see in front of you. So on the left-hand side here, you see an imaging system. So that's an imaging system we have. Now imagine you can do two types of scans. You can do a short scan and a long scan. If you do a short scan, of course, you're going to have artifacts. The image will be a bad quality. If you do a longer scan, you can get up to something that you can call somehow reference. The image quality is better. Now, the simplest recipe that works really well is to say, oh, you know what? Now I have a training mechanism for training an artifact removing neural network. I'm going to take this image, pass it through the neural network, and try to predict this image. All right? If you do this, you're going to end up with something like this. This is an output of the neural network trained to reproduce high-quality reference given artifact image. And this kind of neural networks have been used a lot. This was a very basic way of using neural networks in the context of computational imaging. And this has both advantages and disadvantages. So in this context, let me ask you guys, and I'm going to open this to you guys to get the answers. So what are the advantages of this approach? Can anybody tell me advantages of using artifact removing neural networks for image formation in this way?
Well, you can, you might not have taken care of some details of your system in your mathematical model, but now you can, learn that using data.
Exactly, exactly. So essentially, you might not know all the details, and you just use a neural network as a box to address those, and it in principle learns those directly from data, right? So that's a great answer. So by the way, many answers. I'm going to give you a couple of them. What I kind of came up with, 3 short ones, but there are many. Any other advantages people see?
I have a question. I'm not what about motion artifacts that are usually problematic with MRI data, or artifacts caused by like implants?
Yeah. What about them?
So what about, like, can you somehow like design a network architecture that can remove that?
Well, people try.
Yeah.
I wouldn't be bold enough to say I can, but I try. And some of those things we tried are more successful than the others, and that's what we report. But yeah, motion artifact removal in MRI is one of my pet interesting problems that I work with. Because just in that case, the data is naturally subsampled, dramatically subsampled. But yeah, people work in that. You can try to design those things. We're going to talk a little about that. But
yeah. And what about, there is some, I think from France, there's this company, or from London, they have developed this mini MRI machine that can use intensive neonatal care units. Basically, the Tesla or the magnet strength is very low. Like, I think it's like a one Tesla machine, or lower than 1 Tesla. And then because of that, the images are very blurred.
Yeah, so the SNR basically drops.
Yeah.
So, I mean, that's look, all these problems you're saying can be formulated as an inverse problem and use kind of approaches to address. They all can be put together in a same mathematical language and addressed, right?
So I think those might be some of the advantages that this kind of approach, you can apply that to that kind of data. Like noisy.
Exactly, yeah, you can definitely apply it to that kind of data. So by just feeding it by bad examples here, having some good examples, say you apply for both, right? So definitely. And you can do these things also simulation or experiment.
Mm-hmm.
So yeah. Maybe one more, if anybody has any other idea, what could be advantage? Then I'm going to give my own examples. Hey, yeah, Gia, I think wanted.
Yes. So you can do a short scan and get a high quality image.
Yes, definitely. Very easy pipeline to do everything computationally, basically. You don't do it in hardware. You get a short scan and suddenly the CNN kind of compensates for that and gets you imitation of a long scan, right, to the best of its ability. So let me give you like 3 advantages I came up, like very, very easy implement and deploy, right? You pick get TensorFlow, PyTorch, read a bit about Python and then try to get it going. So that's very easy to implement. Very fast at test time in principle, right? You just pass through a CNN. If everything on a GPU could be pretty good, versus doing a traditional optimization, going through physics and so on, could take hours depending on the problem, right? And advantage 3, so no need to, that's what Wahid was saying, no need to explicitly model anything. Everything learned automatically from data, right? So those are the 3 advantages I thought of, but there are many others. How about limitations? Can anybody tell me about limitations?
Potentially, if there's error in the learning, adversarial examples, etc.
Definitely.
You may get wrong results.
Yeah, if training data doesn't match to somehow in statistics in the test data, you might actually get surprises, right? Definitely. Anything else?
I think being supervised is one of the disadvantages, I guess.
Definitely. Sometimes you cannot supervise. You don't have stuff to supervise. And then you have to come up with ways to not supervise. If you can, sometimes you cannot. So anything else?
You're leaving huge prior knowledge on the table.
Yeah. Definitely, definitely. Yeah, those are all great answers. So they're all related to what I put. So one thing is like we're not exploiting any known physical model. So I told you about the forward model. People spend time modeling MRIs, understanding tomography, right? This approach doesn't use any of that. It just comes from the data. It's advantage and both disadvantage. We're not using it, we're relearning it, which also somehow limits interpretability because what's the capacity of those things to learn? Needs ground truth for training. We heard about it, right? This limits applicability and does not always easily scale to very large problems. So think of very long videos. Think of 4D, 5D data sets. How do we apply it? Well, patch-based, locally. You have to think about those things of how to scale these things to large. So it requires some engineering to get used to, right? So basically, now those are the limitations and advantages. So let me tell you about one way of addressing some of those limitations. Of course, it's not a perfect way by combining model-based optimization and deep learning. And this has been very active area in the past few years. And there are really kind of two branches I want to talk to you about. So, they're on the left-hand side, you see there's models. Essentially, it's physics models. That's what I'm referring to. On the right-hand side, you see the learnings. That's essentially deep learning that I'm referring to. Now, how do we kind of bridge those two things to get the benefit from both? So one very popular approach originated in this idea of plug-and-play priors. This is something I'm going to essentially build on today, where the idea is to have a neural network. You train a neural network, just like what I discussed right now, and you plug it inside an optimization algorithm. You use a neural network within an optimization algorithm, okay? And then if you do this, you're going to end up an optimization algorithm that has also physical component to it, but also uses deep learning as a part of it, okay? And then there are the line of works there, including regularization by the noise, which is an inspiration to the rare framework I'm going to talk to you about, and Simba. And then the reverse idea is based on the idea of unrolling, unfolding. Maybe there are other names to those, but essentially trying to bring models to learning. The idea is you take some model based on optimization, say original paper was LIST, as they took this iterative shrinkage thresholding algorithm, that's Gregor and LeCun. They unfolded it, meaning every iteration of that algorithm was interpreted as a layer of a neural network, and you train it as a learning algorithm, as a CNN, right? And then, of course, there has been lots of follow-up works in that area. And then the SGDNet, I'm going to talk to you about, kind of falls into this as a second scheme. So those are the two grand schemes. Of course, there has been a lot of activities there. There are many papers I didn't mention. I just gave you some pointers about some of the papers. So yeah, and basically in that scheme of things, the first thing I want to talk about kind of falls within this first branch here. It's regularization by artifact removal approach. So let me explain you this idea, right? So we discussed how to train artifact removing CNNs, right? So in medical imaging, you can give a bad example, have a reference, and you train a neural network weights to try to reproduce as good as possible the good examples, try to get good from bad, right? So the key idea, so you pre-train this network, right? Once you have this network, what can you do with it? Well, one thing you can do, you can use it on its own, but let me give you an alternative way of using this network. Okay, and that's the whole idea of RARE. An alternative idea of using that network is to build an iterative algorithm. Okay, so what you see here is an iterative algorithm that really looks like a gradient descent. Okay, X here is an image I want to build. It's an iterative, meaning there's iterations T. And I update my image by doing a negative step towards this G operator here, which I'm going to talk in a second. And it's scaled by a step size parameter gap. Right? So this is just like a gradient descent. However, this is not a gradient. If you look at the definition of the G operator, it has two components. Okay? The first component is the gradient of your data fidelity term. Okay, what is a data fidelity term? It's the term that has a forward model of your imaging problem, right? So Y is your measurements in the say MRI, it could be case-based measurement. It's a sinogram in CT. And H is your forward model. So it's whatever physics information you have on this. And X is the image you want. So the left-hand side here is trying to minimize the data fidelity term, right? Because when it's zero, the gradient, which means we found an image which is consistent with the data that we measured. because this is minimizing this operator. And phi here, just any physical parameters of the measurement system. On the right-hand side, you have a more interesting term, which is residual term. I'm subtracting x from, so input from the output of the CNN. Okay, so what do I want to do with this? Well, think about this. What happens if this is 0? If my right-hand guy is 0, it means the output and the input to the CNN are the same. Okay, which means we identify a fixed point of the neural network. So what is a fixed point? Fixed points are images that are artifact-free according to this neural network. Okay, the neural network is not changing them. It's not acting on them because it's interpreting them as its fixed points, right? Now, this rare framework essentially combines those two. It tries to bring the physical information through the data fidelity term and the neural network through this regularization term, which is a residual term here. Now, here's an important thing. The neural network has been pre-trained. This is not using an untrained network. I'm pre-training networks separately through this process and using it within this iteration. So it's the simplest algorithm you can design that can use both. And then this tau here tells you how much weight you're going to put on the data fidelity term and how much weight you're going to put on the regularization term. Okay, so that's an idea. Yeah, is there a question?
Yeah, 2 questions, I guess. Sorry, this is Anand. First off, why is the image artifact error one-sided? That is, that number could be negative or positive. So what does that mean?
This guy?
Yeah, that guy. And then the other question is, I guess, can't I review that as, could I not sort of try to view that as a gradient of something, in which case G is actually a gradient? I just want to know why you're making that distinction.
Yeah, so by the way, great questions for both. Now, of course, this can be negative, it can be positive, just like gradient, it can be negative and positive, right? So here, we're not talking about positive functions. So essentially what you're looking for is a 0 of this operator. So that's the deep roots of rare lies actually in monotone operator theory for anybody who knows it. But essentially it's about finding zeros of operators. So G is an operator, not necessarily a gradient. I'm going to get to this in a second. It's some operator which might not be a gradient field, but it's an operator, we want to find it 0. So what does it mean when I find a 0? It means I'm finding an equilibrium between the gradient of the data fidelity term and this term here. It could be negative, it could be positive, but I'm trying to balance those two terms, right? And tau tells me how much deviation I'm allowing between these two. If both of them are 0, right, it's still a 0 of this G. If both of them are 0, means you identify the point which is a minimizer of data fidelity term while still being a fixed point of this term on the right. Now, regarding your second question, could this be a gradient? Yes, it can be, but it needs an assumption. And that assumption is that you need a Jacobian of that operator to be symmetric. If the Jacobian of this thing is symmetric, that guy can be interpreted as a gradient of something. And that something becomes an explicit regularizer. Okay, but without it, it's not going to be a gradient. And in fact, if you do this test empirically for some popular neural network models, pre-trained models, you're going to see for many of them, this term, the Jacobian will not be symmetric. Okay, so they're not necessarily the gradients of some explicit term. Okay, but algorithmically, this still makes sense as a equilibrium interpretation between two operators. Make sense?
That was great. Thank you so much.
No worries. Thanks.
So just to follow up, so this iterative form, regardless of what the neural network architecture is going to have a stable point?
Well, yeah, we're going to talk about stable point in a second. So the question is, does it going to converge to a stable point? Yeah. So whenever it does converge, so here's it. Let's divide it into two questions. Whenever it does converge, the point of convergence are the zeros of this operator. So that we can agree with. So when it does converge, we're finding the zeros of this operator. Okay. Now the question is, does it converge? And essentially, that's where monotone operator theory comes in. And in fact, I'm going to talk about assumption in a second. You can show that convergence behavior of this kind of algorithm is very similar to like gradient descent. It's going to have this kind of sublinear 1/t convergence rate for convex data fidelity term, like this one. So not this one, for example, if there's a null space here, it's going to be just a convex, weakly convex term. So that's, I think, assumption 1 is convexity of the data fidelity term. Assumption 2 is existence of the minimizer, existence of a 0. So there, we assume that there exists a 0 for G. And then the third assumption is that the neural network is Lipschitz continuous with constant 1. Okay, so neural network assumption 3 is a Lipschitz continuous. So that's something you can implement in training using spectral normalization. But basically, if you satisfy assumptions 1 through 3, you can show that you're going to reach the stable point or the 0 set of G operator with the rate 1 over T. And R0 here is a distance to initializer. This is a Lipschitz constant of data fidelity term. This is 2 tau, is this regularization parameter here. Okay, and then another thing you can do, you can actually, this is related to Anand's question, like, can you interpret it as an optimization algorithm? So there are a couple of ways to do. One is through mapping that thing to a gradient. Another thing is if this operator is in fact an implicit proximal operator. So proximal operators are denoisers. So for those who know proximal optimization, but I don't need to get deeper in it, but if it is a proximal operator, you can show you're still doing a minimization problem of the form of smooth, non-smooth type of regularization problem, and you're converging with the rate 1 over T plus this constant term that you can control through tau. All right, so basically you can build some interesting theoretical insights through monotone operator theory by adopting this very simple iterative algorithm. It's really simple. That's the simplest algorithm you can do by using a neural network. Yeah. Any other quick questions? All right. So if there are no quick questions, let's move on. Another thing which is part of our manuscript there is a training of this kind of artifact removal networks without ground truth. And really inspiration for this approach comes from noise to noise. Some people might be familiar. It's a very well-known method by now. Essentially, if you have two noisy images where noises are independent, so you have two noisy realizations of the same images with noise being independent over a data set, by training, supervised training using a noise images directly as labels, you can learn to remove noise. Okay, it sounds counterintuitive at first, but if you look at the statistical argument behind, it does completely make sense. I recommend anybody who's not familiar with the idea, look at noise to noise paper. But basically, within this paper, we use the same idea by having several differently subsampled artifact corrupted images maps to each other by doing the same idea. So you have a 5-minute scan, you divide it into 5 1-minute scans of different radial lines. Artifacts are very different because angles are different. And then by training this in a correct way, you can get a neural network to remove those and get an artifact removal network. Then you integrate that network into this algorithm. Okay, so I'm not going to go deeper because we're going to run out of time. But I invite you to look into this and a noise-to-noise idea if you're interested. And I'm open to discuss later anybody who is interested. Is there results that we can show you? So let me show just one result. So this is a 5-minute scan. This is a 1-minute scan. You can see artifacts. This is a zoomed-in version of a 5-minute scan. A 5-minute scan was reconstructed by using compressive sensing MRI, which is essentially sparsely regularized reconstruction for MRI. What you see here is the supervised training of a UNet 3D architecture to map this guy to this guy. Right? If you train it, you're going to get this image, which is not bad. It's a very easy way to use. If you train without using this reference, using two artifact corrupted images to each other in a noise-to-noise style, this is what we call artifact to artifact, you're going to get this. You can see it still doesn't perfectly remove the artifacts. You can see some streaks. But now if you plug this guy into this iterative rare algorithm, it's going to clean it up and you're going to get something nice like this. So this is another example of a different participant. You can see by iterating, you can kind of clean up the image quite significantly from starting from the, by the way, you don't need many iterations. The reason you don't need many iterations is because the initialization is an output of a neural network, which is already pretty good, right? From there, you just iterate a little bit to refine your solution. All right, so that was the first part of my talk, essentially. That was a rare algorithm, very simple, but kind of has nice, elegant roots in monotone operator theory. And I really enjoy working along that direction. Now, the second work I want to talk to is SGDNet, which is essentially going to be trying to build an unfolded version of that rare algorithm, right? I didn't tell you, we trained the neural network in rare by simply mapping artifact corrupted versions to each other. But the question is, can we do a better way of training a CNN, the prior in this thing? And yes, you can get inspired from meta learning or Lista to try to train a better artifact removal operators. And this is kind of what we're going to try to do with SGDNet work. Okay, so first let me start by introducing this idea of a Simba, which is just an extension of what I just told you, rare, to larger scale problems. Okay, so one limitation of the algorithm I just told you is that it uses a full gradient of the data fidelity term. All right, it just uses a gradient of the data fidelity term. And if you have a very data fidelity terms that consist of many, many measurements, just like in optical tomography, where you can have 1 megapixel images and hundreds of them, computing the gradient of this G would be quite slow. So what we want to do is essentially replace this by doing stochastic approximation and computing the gradient of mini batch data fidelity terms. So this is familiar to anybody who has worked with stochastic algorithms or incremental algorithms, where you try to do things on a mini batches. So here, LB selects randomly, uniformly at random indices, and we're going to pick B indices and take the gradient of that. So that's essentially the idea of Simba. It uses only mini batch B measurements per iterations instead of the full set L, making it independent of L. Otherwise, every iteration of your algorithm, complexity grows linearly with L, right? So by doing stochastic processing, you can kind of cut it, which is a very easy concept, but algorithm stays the same. It's the same algorithm, except I don't use anymore the exact gradient at every iteration. I use a mini batch approximation. I mean, nice thing about it is that you can, again, go back and use the same theories that we just talked about and show that it behaves essentially like SGD, right? By using monotone operator theory, you can say that that algorithm will converge roughly as 1 over square root of T in terms of the towards the 0 set of the operator G. Okay, so the algorithm is still stable, it's useful, you can do. And another advantage is now you can do all kinds of implementations of it. You can do synchronize, asynchronous, block implementation and so on. I'm not going to get into the details, but all these things can be found. Yeah, put in our this new iClear paper, which is about asynchronous implementation of this kind of algorithm. But I'm going to kind of skip this a little bit. So basically, the key thing is that if you do this, you're going to get significant accelerations by using multi-processor architectures and decomposing updates and so on and so forth. So here, you have some examples. You can get the same performance, but at much higher speed. So instead of getting 1 hour, you can do in minutes, so acceleration of 8 sometimes. And then we really applied it to experimental data. So this is an example of intensity diffraction tomography, which is a collaboration with Leitian, where you have 6 algae, and I'm showing you 3 slices across. And there are 2 things you can notice. One, this algorithm uses deep learning, so DNCNN as a regularizer, so pre-trained DNCNN as a regularizer, which allows it to get much better optical sectioning in this challenging problem. And the second is that it's actually, if you do this faster processing by taking only 10 measurements per iteration, you match nearly exactly the performance of the full algorithm, but at a fraction of the cost. So it's really practical in that sense. Now, what I really want to go towards is this SGDNet idea, which takes that algorithm and trains it end to end, right? So if I take the rare algorithm I just described to you, so this is a description of it. So you take Y, which is, for example, sinogram here. You can find and initialize it by back projecting it. So you get this X0, which is terrible. Now you want to make iterative updates by using a pre-trained neural network and then gradient step, right? So this gray box here is a single step of that rare algorithm that I show you, which has X minus gamma times gradient plus tau times X minus R theta, right? If you write this down, you're going to get this, right? And then it's iterative, so we can run Q iterations of this algorithm. Now, unfolding means I'm going to interpret each iteration of this as a step in my neural network, a layer, and I can train it end to end in a supervised way. Right? What does this mean, training? I'm going to update this weight theta by trying to imitate this. Now it's going to be a nice network because it's going to have both physical data consistency layers and regularization layers, R theta. So I'm training the weight of theta within this model. Now the SGDNet idea is to take this unfolded architecture and simply doing its stochastic approximations within data consistency layers. So in every layer here, instead of using the full gradient, we're going to randomly select a subset of measurements and have a mini batch approximation of the gradient. So that's why it's called SGDNet, because gradients within this new network are like stochastic gradient methods, or stochastic approximations. And then you can use this and train this, and it's really going to cut down your training time and reduce the complexity of the network. And then, you know, I'm going to not show this, but inside the paper, if anybody's interested, we show that you can train basically SGDNet to approximate the full unfolded rare algorithm to any desired precision. You can put some theoretical analysis to this thing by using stochastic approximation theory. But essentially, the point here is you can, by training in this way and reducing the complexity of data consistency layers, you can cut the training time sometimes by a factor of 2 or more, right? Because it depends how expensive is your physical model, the forward model of physics. There are some examples, because we have not too much time. I'm not going to spend too much time on those. I'm going to invite anybody to look into the paper. But the point is this: by simplifying the data consistency layers, the gradient layers to mini batches, you really can accelerate, and the acceleration depends on how expensive was it to compute your gradient in the first place inside that layer. All right, and then the final, the last but not the least, let me talk a little bit about the idea of coordinate-based internal learning paper, which is we recently put out on the archive. Anybody interested in the details, you can go online and Google it up and find it. Essentially, the idea is to as follows. So, if you think of traditional imaging pipeline, you want to, you collect some measurements. So this is human body, for example, this is tomography. You're going to get a bunch of measurements and you're going to get some data representing. So those are the measurements for each angle. You're going to get 1D function. You put them all together, you get a sinogram here, right? So if your imaging is accelerated, your data will be subsampled. Then what we do, we're going to put it through an algorithm like RARE or any traditional algorithm, which is going to reconstruct an image. And depending on the algorithm, might be artifacts or might be less artifacts. So, possibly with artifacts, but you're going to get some image here. So the idea of COIL, which is coordinate-based internal learning, is as follows. What we want to do is we want to learn a representation of the measurement field. Okay, so what is a measurement field? Measurement field means for every coordinate of your measurement system, so geometry of acquisition system, there is a response. That's what your sensor sees. What we want to do is we want to learn a mapping between the coordinates and the responses. And the mapping is going to be a multi-array perceptron. It's going to be a fully connected neural network. It's not going to be convolutional, it will be a fully connected neural network that we're going to try to train. And what we're going to do, we're going to train it only on the measurements. There's no training data sets. It's going to be an internal learning method, which is we collect subsampled measurements, and for each coordinate response pair, we can use it as a training data for this multi-layer perceptron. Now, once we train this network, we can query it at any location. So essentially, it's going to act like an interpolator, but the neural network interpolator. We're going to query different coordinates and can try to interpolate this measurement field and try to get access to the full measurement field. Now, the idea of this approach has 2 routes. The first route is this paper by the team of Mikhail Irani, which is Schocher et al., zero-shot super resolution using deep internal learning, right? Internal learning concept means you try to learn from a single test measurement itself. You don't have a separate training data set. You use that single measurement to learn. Now, why is it possible? It's possible because images are very often self-similar. Within one image, you might have repetition of information. Okay, and that was an idea used in this paper in the context of super resolution. Since I heard that talk and I'm a big fan of this work, I never could come up with a way to use it for more general inverse problems, because the properties they used were very specific to super resolution. They used the fact that subsequent blurring kind of reveals that multi-resolution information inside the images, and they used it to train their convolutional neural networks. Okay, but it's a very elegant paper. Now, the second root of this idea is a NERF paper, which is right now a very hot topic, which is basically representing scenes as neural radiance fields, right? So essentially, this idea of having coordinates to response mapping comes from NERF, right? Now, what we do is we use essentially this coordinate-based representation to use internal learning of the measurements. And that's the key idea of the coil frame, right? And now, once you, in fact, do this, here's a full pipeline. You collect subsampled measurements, you pass it through the coordinate-based MLPs, that's going to get you a full field. And now you're going to combine these two and put your favorite image reconstruction algorithm to try to build images. Okay, it can be really combined with almost any image reconstruction method. And then the key things that we observe is that it really consistently improves any image reconstruction method. Okay, so here's an example. On the left-hand side, so this is an example with sparse view CT, where you have 120 views of an object at 40 dB SNR noise. So there is noise and there is subsampling in the views. Okay, so if you just do filter back projection, you're going to see this. Now, if you use this pipeline and just get a multi-layer perceptron to bring it to 360 views and use coil filter back projection, you're going to get this image. You can see this drastic improvement from left to right by using this internal learning mechanism. And here's some zoomed in images. You can see it really significantly improves. It's not perfect because the algorithm is very simple. It's filter back projection, but you can see the boost because of this. It's pretty significant. Now, of course, you're not restricted to filter back projection. You can use it also with another algorithm. Say this is a traditional algorithm called total variation regularization on the same data. So, we move from filter back projection to total variation. Now you can see that it has these blocky artifacts, which are very well known for total variation. You can see there's kind of cartoonish features. And then the coil here still has those features, but kind of improves to mitigate. You can see it improves the performance. And in fact, total variation has been fine-tuned for both examples separately. So this is the best performance you can get. This is the best performance you can get for total variation. So coil for free improves user performance of total variation, right? Now, of course, you can combine it with regularization by denoising or rare. So this is an example where we train a CNN, the CNN prior, put in the iterative algorithm, and try to now there's two things. There's multi-layer perceptron, which tries to get the measurement field, but there's also prior information, which has been learned separately, pre-trained separately. So if you have no coil and coil, you can see it gets rid of those blockiness by improving, and having coil actually improves the performance quite a bit. You can start seeing a lot more features in those images. And finally, you can also combine it with traditional neural network architecture. So this is a UNet architecture trained for artifact removal. If you kind of put it through the coil, improvements. I guess, as you can see, as your method gets more and more sophisticated, the improvements, of course, become more and more marginal, but there's still non-negligible improvements at every case. So basically, for free, you're improving any image reconstruction method by using this idea of internal learning. So I think at this moment, I would love to conclude my talk, and maybe I'll have a couple of questions afterwards. We covered a lot of things, but essentially three things. First was simple idea of using CNNs as regularizers within an iterative algorithm. The second was using mini batch approximations within them to improve computational complexity, and then using them as an unfolded networks. And finally was this inspiration of internal learning and coordinate-based representations to bring them together to represent the measurement fields for computational imaging. Thank you, everybody, for joining, and I'll be happy to take any questions if there are any.
Well, thank you, Ulugbek. Let's thank the speaker for the wonderful talk. So we have some time for questions. I do have some questions of my own, but since I'm meeting Ulugbek later, I can postpone those questions for that time if others have questions earlier. So anyone has questions? Okay, let me then maybe jump in. I want to go back to the topic of physical models, right? So far what we have seen though is majority of the times or almost all of the time actually there has been no explicit use of the forward model. What has been used is really the data fidelity term. So doesn't that suggest that there is more that could be utilized from our knowledge of the forward model, like where or could we add more physical model, or is there something I'm missing and physical model is somehow being incorporated in this that I didn't fully catch?
Yeah, so the way the physical model is completely part of it, right? So data fidelity term has a physical model.
Oh, okay.
Since it is part of it, so this gradient here, if you take a gradient, it's going to be H transpose H X minus Y, right? Essentially, we call it data consistency layer. It becomes, well, a data consistency step, right? It has a physical model. Now, cost of computing this, of course, depends on the cost of computing that physical model.
But what about other, I guess maybe I shouldn't call them physical models, like maybe other prior physical knowledge, like, if you're like, it doesn't seem there is any exploitation of perhaps sparsity or other smoothness properties or any of those other details.
No, so yeah, so you're right. So like within the physical model, we're not using any like properties, like say, how do you say, geometric properties of physical models. We're not decomposing, but here's the deal. In fact, this is such a great question because that could be done, right? This kind of suggests you whatever models you could have, you could integrate it in similar kind of framework by embedding, for example, instead of parameterizing directly in this way, you could parameterize in terms of something else here and represent this physical model through another layer of representation, if it is interesting in your problem. But I haven't investigated that, but this is a great question.
Okay, great. Thank you. Other questions?
Yeah, so maybe I have a quick question to Ulugbek.
Sure.
So in terms of noise characteristics, in terms of robustness, in terms of noise, if I were to compare L1 based denoising and rare, so what will be your comment on that?
Oh yeah, so rare is going to be much better. Okay. And then the reason is not, something inherently superior to rare or something. It's because just neural networks, the way they characterize those images, is, there are several advantages they have. The first advantage is that they can be data adaptive, right? So you can adapt it to specific, like MRI data, you can adapt it to MRI data. You can use dictionary learning to do the same thing for sparse representations, but it's not going to be as powerful empirically as neural network. And this is not only me saying, there's just a lot of empirical evidence out there for that. So if you just use sparsity-based representation versus rare, you're going to actually, here's a little, let me go here, because we do have actually examples of that here. Explicit example empirically gotten. So let me come here. You're going to see typical, so total variation is an example family of sparsity-based methods.
Yes, exactly.
So it's a gradient domain sparsity. So, and in this problem, the regularization parameter has been fine-tuned for the best SNR performance. So this is what you would see with and without coil for both, right? So if it's no coil or coil, both cases you see something like this for this example. Now, if I would use this red, which is essentially a rare, but where I have a denoiser as a prior, it's a CNN trained to denoise, I'm going to get this.
Okay.
So there is a boost of about, I don't know, like a 1 dB or maybe a little more than 1 dB in this case by using CNN as a prior. Okay. Yeah, so it's typically you get empirical improvement by putting in CNN.
Okay, so in future, everyone is going to use rare-based denoising than CS-based denoising?
Well, I wouldn't go as bold to claim that, because there is a world where we don't want to train. There are cases where we don't have training data. There are cases where we have a lot of different settings where sparsity-based denoising plays an important role. So, it's just a different methods, at different settings, you might find them more useful or less useful. So, I'm not, very let's talk about any one of them.
Okay, thank you so much.
No worries.
Okay, well, so it looks like we are out of time. So let's thank Ulugbek one more time for his wonderful talk, and we'll see you in 2 weeks for the next SIP seminar.